Look around you. Everything you see in this room, the screen you're watching this video on, and me, it's all made of matter. Sounds obvious, but this is one of the greatest mysteries of physics today. A good place to start is the Standard Model, our best theory of particle physics to date. It can describe any kind of particle interaction you can think of, but we know that it cannot be the full picture. Alongside problems like not knowing about gravity, the Standard Model does not have enough of something called CP violation. It's clear that we need new physics, and the question is what to do about it. The first thing we can do is the direct way of searching for new physics. In this case, we go to our particle accelerator, collide some protons together, and hope to produce the new particle we're looking for, which is what the Large Hadron Collider does at CERN. But in this way, we are limited by the center of mass energy reach of our collider. This brings us to the second option, the indirect search for new physics. It's more like a crime scene investigation, where you don't get to observe the particle you're after directly, but instead you trace its fingerprints in very precisely measured and very precisely calculated quantum phenomena. This is what Flavour physics does. At the heart of Flavour physics lies CP violation. Think of matter and antimatter like mirror images of each other. In theory, we have no reason to believe that the laws of physics should work differently for them. But in this case, there would be equal amounts of matter and antimatter in the universe, then they would meet together to annihilate, giving us a universe made of pure energy, which our seemingly trivial observations showed us that this is clearly not the case. There is indeed a tiny little mismatch between the behavior of matter and antimatter, which we call CP violation, that the Standard Model has. But this amount is nowhere near enough to explain our observations. Me and my colleagues worked to find a solution to this problem studying the D meson. D meson is a particle made of the charm quark and a light antiquark. But when charm quark gets involved, things get complicated quickly. Charm quark is both too heavy and too light at the same time to precisely describe. Our best theories let us down in this mass regime. On top of that, the Standard Model observables for the charm quark suffer from huge cancellations, shrinking the size of anything we can hope to measure experimentally or calculate theoretically. Because the Standard Model observables are small, any deviation we can detect from it, no matter how tiny, can be a clear sign of new physics. This year, we focused on the D0 to K-short decay. After days that turn into weeks that turn into months, we managed to come up with a theoretical expectation of CP asymmetry that this decay has, and we found 0.1%. If experimentally it will be measured to be much larger than this, there is no way the Standard Model could explain that, and that could be the hint of the new physics, the missing source of CP violation we're after. In the months that followed our calculation, our experimental colleagues at the LHCb collaboration did measure this effect, and they found 1.8% consistent with zero within uncertainties. So, does this measurement point towards the Standard Model or towards new physics? Unfortunately, the current precision doesn't give us a clear answer. But this summer, the Large Hadron Collider is going under an upgrade, and when we turn it on again, we will have many more collisions, much more data, and much better statistics. Then we'll be able to answer this question as well as many more. The particle animations you saw in this video are made by us and available publicly on GitHub. If you would like to know more about our results, you can find the paper on arXiv, and it is also linked in the description. If you have any questions about what we presented today, please leave us a comment.